In this section, we'll be looking at how to determine order. If we're looking at a rate law, rate is equal to K. Let's say I have two reactants, A and B. So the reaction would be something like this. A plus B goes to product. And let's say the ratio is 2A plus 1B goes to products. The mole ratio, 2, does not mean second order. The only way for me to do this is to set up an experiment, and we will want to change concentration of A and B, and then make some observation about rate. Does it go up? Does it stay the same? The steps to this process are listed here. First, we're going to use either the algebra or the calculus-based method. This video, 13-2, we're going to go over the algebraic form, and in the next video, 13-3, we'll look at the calculus-based, the integrated rate laws. Okay, so there's more than one way to do this, and there are advantages and disadvantages to both. We're going to determine order with respect to each reactant. So that means that I'm going to have to do some isolation experiments. That means change the concentration of one reactant at a time. For those particular reactions that have more than one reactant, A and B, for example. Then we find the rate constant, K, and write the rate law. Once you have the rate law, you can solve for rate at any concentration. All right, so that makes it a valuable thing to do. Right, on the following slides, we'll look at two different examples and solve for order, rate constant, and write the rate law. As a reminder, let's talk about what this means. Let's look at a reaction of A going to product P. So we know that the rate law will be something like this. Rate is equal to K times A to the X power. So if X is equal to 0, the reaction is 0 order, then rate is equal to K times A to the 0th power, or, let me erase this part here so I'm not overlapping, or, to simplify that, rate is equal to K. Remember that as we increase A, there is no change in rate. Right, so that's one possibility. The second possibility, if X is equal to 1, rate is equal to K times A to the first power there, or I can just write rate is equal to K. Let me go ahead and erase again. Whoops. Rate is equal to K times the concentration of A. And practically this means as A increases by a factor of 2, rate will double. Right? So they're a 1-to-1 relationship. The third possibility is that X is equal to 2. So in this case, rate is equal to K to the second power, or squared. So practically, as A increases by 2, then rate will quadruple. So it's a 2-to-1 kind of relationship. Until we look at the data, we don't know if x is equal to 0, 1, or 2. It can be any possibility. It just depends on the nature of the reaction. There's not one answer that's more right than the others. It is simply a matter of what is the chemical property of that particular reaction. Let's talk for just a minute about how you would do this sort of experiment in lab. And you guys are going to do this at some point this semester. Right, so let's say I have a test tube, and I'm going to put my reactants in there. Let's say I've got 2 components, one component. That's how it's written here. All right, A goes to product. And I know it turns, it's a really bad test tube. Let me see if I can redraw that. Make it look a little bit better. And I know it goes from clear to yellow, let's say, for example. So what would happen is I would put my reactants in the test tube at a certain temperature and hit the timer and time how long it takes to completely change colors, or at least be a consistent color. And so some of this you have to do some trial and error to decide what is going to be the stopping place, and you want to keep it consistent, of course. All right, then you would write down the molarity of A, how much you put into the test tube, and the time it takes to do that, and we do a conversion of rate, which would be molarity divided by seconds, let's say. And so you have your two different sets of number here that you'd keep in a chart. All right, that's trial number 1. And then in a separate tube, I'd have to start over from the beginning. I would put in twice as much. Let's see if I can erase here. It's not wanting to let me erase, so so trial 2, we would put in twice as much, and again we're waiting for it to go from clear to yellow, and we time it. And do the calculations, molarity per second, and so on and so forth. And so each trial, you would have to have a separate test tube and time them all separately. And then you could compare data to determine order. Here's our first example. What we're going to do is we're going to find order, write the rate law, and solve for K, and then write the rate law again. All right, and so this is reactant A going to P, and I know the rate law is going to be rate is equal to K times the concentration of A to some order. Right, so it doesn't matter in this case because I have one reactant. I could compare either trial 2 and trial 1 or trial 3 and trial 2. So let's do 1. In this case, we need to put the larger number on top, so we're going to do 2 to 1. So I need rate 2 over rate 1 is equal to A2 to some order over A1. All right, so I'm going to plug numbers in here. Rate 2 is 0.030. Rate 1 is 0.015. Concentration of A and 2 is 0.2, and N1 is 0.1, right, to some order. So I solved the numbers. 0.03 divided by 0.015 is 2, and 0.2 divided by 0.1 is also 2. Okay, so in this case, what is going to make this a true statement? Is x equal to 0, 1, or 2? If it's equal to 0, so if 2 is equal to 2 to the 0th, that's the same thing as saying 2 is equal to 1. So that is not a true statement. If 2 is equal to 2 squared, then 2 would be equal to 4. Again, not what it says. So in this case, it would be 2 to the first power, or 2 is equal to 2. So now I know it's first order with respect to A. Okay. So let's go ahead and erase here. All right. We'll write rate is equal to K times A. And if it's raised to the first power, it's the same as the concentration by itself, so we don't need to write that 1 in there. Now we want to solve for K. So I'm going to plug in a number for rate and a number for A. My only thing I need to be careful here is if I use the concentration of A from trial 3, then I have to use the rate from trial 3. It doesn't matter which one I use. I can use data set 1, 2, or 3, but I have to use the data that matches the trial and the rate number. All right, so let's use 3 since we're talking about that one. So my rate is 0.060 molarity per second is equal to K times 0.40 molarity. Right, and I'm just solving for K, so I'm going to divide both sides by 0.4 molarity. And those molarities will cancel out there. So 0.06 divided by 0.4 equals 0.15 per second. Now I can write my final rate law. Rate is equal to 0.15 per second times the concentration of A. I could plug in any concentration of A theoretically and solve for rate, which is why we go to the trouble of doing the calculations and writing the rate law. Right, here's our second example, and it's a little bit more complicated. It's 2 variables. We have NO2 plus carbon monoxide goes to product. Doesn't really matter what it is in this particular instance. So I'm going to say rate is equal to little k times the concentration of nitrogen dioxide to the x power times the concentration of carbon monoxide to the y. All right, so I have to find both x and y. And I have to do them separately, where I can only change one variable at a time. Okay, let me show you what I mean here as we look at the data. Right, I have the concentration of nitrogen dioxide here and carbon monoxide here. Right, so let's look at trial 2 and trial 1. In this case, we have only changed nitrogen dioxide. Carbon monoxide is staying constant. So in that case, I could solve for the order of nitrogen dioxide. Now, if I look at, let's say, trial 2 and trial 3, all right, in this case, nitrogen dioxide is staying the same and carbon monoxide is changing. So this will allow me to isolate each variable. Okay, so for nitrogen dioxide, I'm going to use trial 2 and trial 1. So rate 2 over rate 1 is equal to 0.0082 divided by 0.0021. And the concentration, I don't have to worry about carbon dioxide here because it does not change. I'm only looking at nitrogen dioxide. It's carbon monoxide. I think I misspoke there, but all right. And this is to some order x. So I do the math and I get 4 is equal to 2 to the x. So to make this a true statement, x would have to be 2. Or another way to say that, 2 squared. 2 times 2 is equal to 4. So now I know the order for nitrogen dioxide. It is second order with respect to nitrogen dioxide. Okay, I've got to go through the calculations now for carbon monoxide. Do the same thing. We're going to isolate and compare rate 3 to rate 2. Because in that case, the nitrogen dioxide is staying the same and carbon monoxide is doubling. Right, so it's if I'm looking at 3 first, that would be 0.0083. And trial 2, the rate is 0.0082. Carbon monoxide, 0.2 to the y over 0.1. All right, so I do the math. 0.0083 divided by 0.0082 is 1.01. That's 2 to the y. Okay, so really we round to the whole number. This makes y equal to 0 because 2 to the 0th power would be 1. So 2 to the 0th is equal to 1. Right, so this reaction is 0/0th order with respect to carbon monoxide. Now I can write my rate law and solve for K. All right, I'll erase there. Rate is equal to K times nitrogen dioxide in the second, and carbon monoxide to the 0th. And anything to the 0th power is 1, so we would simplify that further. Rate is equal to K times nitrogen dioxide squared. All right, again, I'm going to solve for K. It doesn't matter which trial I use. I can use 1, 2, 3, 4, but I need to be consistent. I need to use the concentration and rate from the same trial. So let's use trial 4 here. Rate is 0.033 is equal to K 0.40 squared. And so I divide both sides by 0.40 squared. Those will cancel. So 0.4 squared is 0.16. So that becomes 0.033 divided by 0.16. That's equal to my K. And I'm getting K is equal to 0.21 if we're going to sig figs. And this would be, rate is molarity over seconds, and this would be molarity squared. All right, so let's go ahead now and write our complete rate law. Rate is equal to 0.21 per molarity squared times let me redraw that. make that a little bit messy, 0.21 over molarity squared times the concentration of nitrogen dioxide squared. Okay, so that's my complete answer there. You'll do a couple of practice problems in class. One will be a one variable problem, like example number 1, and the other will be a 2 variable, like this example.